Hello everyone, my name is Annika Smith and welcome back to my fifth video of the Stat 231 series. In this video, I'll be going over connecting chapters 4 and 5 together. So what I'm doing is connecting the likelihood interval to the confidence interval to the p-value using a couple theorems that we've talked about in class. So to get right into it, the chance of getting a feature 5-star on a random attempt is allegedly 2%, and Annika saves her currency to decide to test whether or not this is true. So I attempt 180 times and get one feature 5-star. So let y be modeled by the binomial distribution, and assume that my attempts are independent. So the first thing we want to do is derive a 45% likelihood interval for this data. Based on this interval is 2% a likely value. Now recall that the likelihood interval is essentially telling me, okay, in like what scenario, like how likely is it for me to have a certain value of theta given like my actual theta hat or like my estimate of what actually happened. So it's kind of like if you have a really small likelihood threshold, like say like 10%, it's going to be a very wide interval because you're going to have like a lot of different possibilities where it's like, okay, there's like a 10% chance that maybe this theta could be like in for this data set or something. Um, Whereas 45% is relatively high. So we're only looking at like a very plausible, like all the thetas that are like 45% plausible, kind of. So essentially, this is a lot stricter than we might normally see with a likelihood interval, but we can still compute this. So what we do is we're given this graph here, and all we have to do is draw a horizontal line at the 45% mark. So I'm just going to cheat and use a actual straight line here. And I'm just going to put that at the 45% mark. So that looks like it's going to be about right here, say. And then from there, I just want to trace down to the x-axis to see what values of theta this corresponds to. Let's get my purple color. Okay, so this looks to be about 0 over here. And then this part here, it's certainly less than 2%, but not quite sure. So we'll just say something like, how about we're on the interval of from 0 to about, say, 1.9. Or not 1.9, 0.019. So this is our observed likelihood interval. And from here, we're asked, based on this interval, is 2% a likely value? So we look in here and we say, okay, is 2% contained in this interval? And the answer is no. 2% is not an element of the likelihood interval. So we'd say that it's not likely based on this data. So moving on, we want to compute an equivalent asymptotic confidence interval, and based on this interval is 2% a likely value. So what is an equivalent asymptotic confidence interval? An equivalent confidence interval would be one that I have this written on my formula sheet over here, where, okay, so it's a little bit much, but essentially we define our likelihood interval over here as this. So we have the lower bound, the upper bound, and then the relative likelihood function is greater than or equal to some value f. Because we're doing the 45% likelihood interval, our value of f is going to be 0.45, and that's going to be equal to this value here. So this e to the power of negative a squared over 2. So we have everything in here. We need to solve for a. Then once we have a, we can solve for q to get the q% likelihood or confidence interval. So first, what we want to do is just follow the cheat sheet, solve for a. So we have that f, which is equal to 0.45, is equal to e to the negative a squared over 2. Rearranging, I'm going to take the ln of both sides. And the ln and the e will cancel out, so I'm just left with this. And then I can multiply both sides by -2. So then I'm just left with a squared on this side. And then my last thing I need to do is just square root both sides, which this value, note that this argument is less than 1, so this part will be negative and this part's negative, so we actually have a positive root, so it's not going to be some imaginary thing. So we can just stick that in there without any worries. and this is A. So we're just taking the positive root because A is going to be positive. And we can compute this, so plug that into your calculator. I'm going to use R to do this as usual. And we see that A is this 1.2637 value down here. So that's step one. Step two is now we have to actually compute what kind of confidence interval we're using, so this 100Q%. So this is based off of the Gaussian or normal distribution, this probability here. So all we have to do is compute 2 times P of Z less than or equal to this A value is equal to, or sorry, minus 1 is equal to Q for our Q% likelihood interval. So I can go ahead and do that on, well, you'd need to use like either some R code or the table to calculate this probability, but you can see over here that I've computed my A value, and I say 2 times P norm of A minus 1 is going to be Q. And we get that Q is 0.7936, and from there, we're doing 100Q% CI. So essentially, we're looking at the 79.4% confidence interval. So I've multiplied that 100 and that little decimal there. So our equivalent confidence interval is going to be this 79.4% confidence interval. And I have it around here, but in my R code, it's like I'm using all the decimal places. I don't think you'd see anything with like this many decimal places on the exam, but just practice using as many as you can. And to do this, I have another video on computing binomial asymptotic with like all the derivations and stuff. In this video, I just want to jump to the very end. So we have that this is our kind of formula for computing the lower and upper bounds of that confidence interval. So we can just plug in all our numbers here because we know what y is, we know what n is, we know what a is, and it's in fact the a that we already solved for up here with this f and e business. So we can just plug everything in here to find our lower and our upper bounds. So we're going to do, that's 1 over 180, our y over n, plus minus a times the root of 1 over 180 minus this guy here over 180. And then I could just plug this into my calculator again. Again, we had that A was around, what was it, 1.236 or 263. But I can also just do it again because recall it's going to be the quantile for this 1 plus q over 2 probability. And we see that we get back to the same thing. We're just undoing some of the operators we did. And it's a 180. And these are my two formulas here to compute the lower and the upper bound. And we get that it's about 0 and 1.255 or 0.1255. So our confidence interval is about 0 to 0.0125 and 6. So from here, we are asked, is 2% a likely value based on this? And the answer is again, no, because we see that it's not involved in this interval, so 2% is not an element of the confidence interval, so we would not say it's likely based on this data. So for our last part, we are asked to conduct an appropriate asymptotic hypothesis test and compare the p-value that we get from there to the p-value we can derive from the confidence interval. I'm referring to like a very specific theorem we have. I wasn't quite sure how to communicate that, so I'll show you what I'm talking about. But first, let's do the hypothesis test. So let's use our 5 steps. First, we want to define our model. Well, our model is just going to be y is binomial with 180 trials, and we have our theta. Number 2 is going to be our hypothesis, so h naught. We're saying it's going to be theta is equal to 0.02, and we're just doing a two-sided hypothesis again, so our alternative hypothesis is that theta is not equal to 0.02. And then step 3, we want to calculate our test statistic D. So I have that over here. This is our random variable for this scenario. And if we just plug in all the values we have, I'm not sure why that says y bar there. It should just be a y. Oops. And once we plug in all of these, we'll have our little d, and then we can go ahead and compute the p-value for step 4. So we have that absolute value of 1 over 180 minus 0.02 over the square root of 0.02, 1 minus 0.02 over 180 is equal to d. Just checking that looks good. And this is based on the Gaussian distribution, so we can hop over to our code, and you can see I have it written over here. I know there's a lot of variables here, but just to break it down a little bit, this is our 1 over 180, this theta hat here. Theta naught I've defined as 2%, like we've kept saying, and got everything in there. So once I compute that, I see that it's going to be 1.384, and then I can compute my probability. So we've solved D, and now all we have to do is compute our p-value, which is going to be, because this is a two-sided test, it's going to be 2 times p of big D greater than or equal to D. So we have 2 times this p norm of D, and lower tail equals false, so I get that greater than or equal to. Or this is equivalent to, if you don't have this lower tail equals false, you can just do 1 minus p norm. And we see that these come out to the exact same value of a p-value of 0.166. So if you recall from our chart, the lowest thing we have is 0.1, so anything above this, technically our p-value we do not have any evidence against H0 based on our p-value from the chart that we're given, but I do want to talk about this theorem that we have, so just going to write this in here, 0.1663. And I have it written over here. So essentially, if we use the same pivotal quantity to test the 100Q% confidence interval and conduct a two-sided hypothesis test with this H0 of theta equals theta naught, then the theta, if the theta is in there, in the confidence interval, if and only if the p-value is greater than or equal to 1 minus q. So to repeat that, we have to use the same pivotal quantity to construct this, and this is kind of where I was getting tripped up before, but it has to be the exact same pivotal quantity, which we did with the asymptotic one, and we constructed our 100Q% likelihood or confidence interval. We've constructed a two-sided hypothesis test. So the theta that we're looking at is only going to be in the confidence interval if this p-value is greater than or equal to 1 minus q, whatever that q may be, and vice versa. This is an if and only if statement. So we've already determined that theta is not in our 79.4% confidence interval that we just computed. And we found based on our chart that there's no evidence against the null hypothesis. However, with this, we have to compute 1 minus 0.79, whatever it was, which I have over here, 1 minus q, and that's going to be 0.206. So we see that theta is only in this confidence interval if our p-value that we generated is greater than 0.206, and we found our p-value is actually 1.6628, so which was less than this value, so we can see that this theorem holds. That's essentially what I'm getting at here. We did a little bit of this on the R assignment as well. But with all of that, that concludes this video, so I hope you learned something, and let me know if you have any questions or if there's anything I can clarify, and I hope to see you in watching my next video. Thank you.